Yeah, so maybe we'll make a start. So speaker today is Francesco Saettone, who will talk about the Pila-Zannier strategy for Drinfeld modules.
Okay, thank you very much for the invitation, and I also want to thank the organizer of the special year for the hospitality and for having me here. So, yeah, this is a joint work, partially in progress with Binyamini and Dmitry Novikov, and what I want to do today is like to show how the so-called Pila-Zannier strategy can be adapted over function fields and positive characteristic for some relevant objects for which it makes sense to formulate problems in a like intersection. So this will follow the original strategy, which means that like we will need some to reach at some point a contradiction between bounds, an upper bound and a lower bound, and a big part of the work was also like to produce like the relevant transcendental results that we need. Okay, so I will start with some notation. I hope it's readable here for everyone. So we take a prime P and we fix some power of it. We're gonna call it Q as usual. Then by A, I will mean the polynomials coefficients in FQ. By F is fraction fields, so rational functions. So this guy now has an absolute value, so that given a polynomial A, this is defined as Q to the degree in T of A. And we can complete F with respect to this norm, and we get the infinity, which is simply FQ 1 over T. And then once we fix an algebraic closure, we have something which is non-complete. So we complete now by certain theorem of Kressner. This guy is also algebraically closed, and we denote it by C infinity. So yeah, this essentially plays the role of like the integers or the natural, perhaps. These of the rational numbers, the reals, and the complex. Okay, so I will define an A field, a pair L with iota, where iota is an embedding of A. I'm gonna suppose it's like injective for the sake of this talk into L. And so right. And for the endomorphisms of GA over such a field, tau will denote the Frobenius. Simply takes like respective coordinate to x to the q. Right, and as a left module by composition, this is actually isomorphic to the skew polynomials coefficients in L, where this is like the non-commutative ring of polynomials in the Frobenius, such that tau of A equals A to the q tau for every A in L. All right. So it's almost readable. Okay, let me start with some refresher on Drinfeld modules, which are like the main gadgets we're gonna use. So refresher on Drinfeld modules. So historically, these objects which I'm going to introduce were obviously introduced by Drinfeld, although in one case was already studied before by Karlitz, and they played like the main role in the Langland's conjecture for GL2 over function field, and also their Stuck incarnation. So they've been widely used in number theory, but also they share like some geometric construction and characteristics, obviously with some cases with elliptic curves, in others with abelian varieties. And it's possible to do some Diophantine geometry over those. In particular, this was started in the 80s by Denis. So I will denote a Drinfeld module over L by this capital curly D. And this essentially consists in an algebraic group G, which is isomorphic to GA over L, and in a phi, which is actually the module action, which I'm going to define, where phi is an FQ algebra map of A into the endomorphisms of GA over L. This is a morphism I said before. There's two polynomials. We require that this is like FQ algebra. And so we have this morphism such that the degree as a polynomial in the Frobenius of f is bigger than 0, and the Lie derivative of phi, of phi of t equals t. So what does it mean? It means that like we have here a polynomial. The map is going to send like t. It's going to be determined by t because it's a PID. Some endomorphism, phi of t, can be written as t plus g1 tau plus gr tau to the r. And we ask that at least one of these GRs is non-zero. So we can define the rank of the Drinfeld module as the degree in tau of phi of t. And yeah, okay. So let me note that by this definition, we can define Drinfeld modules for every rank. And we're going to see also like what it means at the level of analytic uniformization. Okay, so given two Drinfeld modules, we can take their Cartesian product in the prime, it will be just A over L squared. I suppose they're defined over the same L. And we'll take just the Cartesian product of their module actions. And this is gonna be like, this is gonna be the ambient space where we're gonna work and produce our results. And it can be thought, of course, like intuitively, if we stop like our rank R to 2, we're gonna see that like they correspond, like they share some analogies with elliptic curves. And so this can be thought as a product of two elliptic curves over, of course, function fields. So let me also define a Drinfeld submodule. So H, or maybe a sub-Drinfeld module, to be a connected algebraic group. Or maybe the separable closure, but such that it's stable under this action, which I will call capital Phi, which means that P of A of H inside, well, P of T of H is contained inside H, so it's stable. So this is indeed not the most general thing that one can do when you raise the dimension. There's also the notion of T modules or Anderson modules, but which perhaps is like closer in some sense to abelian varieties, but like trying to give a proof of concept, we are going to focus only on this. Okay, so let's see the equations. So I keep recalling some notions, in particular, some rigid analytic uniformization, better, it's the infinity uniformization. Okay, so we're going to consider lambda to be an A lattice in the infinity, which means, as usual, like, well, finitely generated, discrete, projective A submodule. Of infinity. Now, like this can be written, prefix like a base, as just like fixing a base of C1, CR. This can be written just as like the direct sum of the CIs. Okay, this can be thought of like an F-infinity basis, for instance. And so a first remark, which is how interesting, although simple, is that since the degree of C infinity over F infinity, so the complex over the reals in this case, is infinite, you can get arbitrarily large lattices, since there is no maximal dimension. And this obviously will correspond to the fact that I said before that we have polynomials of every degree. So there are lambda of any rank. Okay, so this is all the work of Drinfeld in fact. And in particular, Drinfeld showed an equivalence of categories, which is just an isomorphism between, bijection actually, between Drinfeld A modules of a fixed rank over C infinity, or isomorphism. This is like bijection with A lattices in C infinity, the same rank up to a month indeed. Okay, so we need to recall how to construct such a thing because it will involve like an exponential map. But as you can see, this not only not a perfect indeed, but it shares strong similarities with elliptic curves, but even with GM, in particular GM when we're going to take the rank to be 1. And then there are like higher rank objects which have no counterpart, at least whose counterpart in like the characteristic 0 word is not known. So let me define the Drinfeld exponential attached to a lattice, which is going to be an analytic function over C infinity, simply in this way. Lambda and lambda on 0, 1 minus Z over lambda. So like this guy is really an analytic over C infinity. So it means like an expansion and it converges everywhere. And yeah, it's gonna play the role in the case of like rank 1 of the complex exponential. And in general, it plays the role of the Weierstrass phi function. So this function is constructed so that its kernel is lambda is given by the lattice. And although it is highly transcendental, it has the amazing property to be additive. Which means simply that the exponential of A plus of maybe Z plus Z prime equal exponential of Z plus exponential of Z prime. And it's of course also FQ linear. Okay, in particular, it satisfies like, so, okay. One can then show exactly how to construct such a bijection. In particular, this follows from like the fundamental functional equations, which says that like, so this map goes to C infinity to C infinity. So the action of T upstairs, which is like just a multiplication, is given by the Drinfeld module actions downstairs. Like quality is really fundamental for the construction of this guy. This means, like in more familiar terms, perhaps, that we have the following short exact sequence. So we have a lattice which embeds into C infinity and which projects the exponential to C infinity modulo lattice, which is still isomorphic to C infinity. So in fact, here we can think of like the lead of GA over C infinity, and this guy has like the C infinity points of our Drinfeld module. So this is going to be our covering and uniformizing method. Okay, so I want to give here like one example that we're going to use later. Of course, if there are questions or comments, please feel free to interrupt. So the example is like for rank equals 1, which means like, well, we don't have a lot of choice, right? It has to start with T, our Drinfeld module, and then to have like a Frobenius. Of course, one could renormalize things, but this is called the Carlist module. Was already studied by Carlist, and can be interesting also from point of view of like class field theory. And yeah, and of course its lattice, well, can be renormalized. Let's say that it's like this, where this pi corresponds, it's a transcendental element which corresponds to that's 2 pi I. And of course it has to be written like, it has to be written as like rather complicated power series in T, Q minus 1, and then we take the product 1 minus T, Qn minus T, T is Qn plus 1 minus T over N. But of course we can like renormalize it so that lambda will be just A. And we're going to use this as like as a test case also to work with some examples. And of course, once you renormalize here, its Carlik's exponential is going to change a bit according to its period. So, but at any rate, this is like the analog, can be thought in many senses the analog of GM. So the upshot, what is the difference between Drinfeld modulus and elliptic curves or even GM? Well, first of all, like the geometry, right? Because here the geometry is rather simple, it's just J. But for the others, it's rather complicated. But more schematically, like we can say that elliptic curves have a cumbersome and perhaps rather complicated group law, which is given by the arc-tangent construction, and a very simple Z module action. They are just Abelian groups. On the other hand, here, Drinfeld modules have a very simple group structure. It's just J, but a rather complicated A module action. So yeah, there are parallels, but the substance is really like different. All right, so now the strategy has been developed for many situations, starting from Manin-Mumford up to Silver-Pink. In this talk, I'm going to talk about some version of Manin-Mumford for Drinfeld modules, and then another case of André Oort. And in particular, our version of Manin-Mumford, which was, by the way, already proved by Scanlon 20 plus years ago using model theory, will be for the product of two Drinfeld modules, although we are working to generalize it to an arbitrary product. So let me recall, is it readable here? What are torsion points? So we take a polynomial, perhaps not zero, and we define the A torsion, something as like the elements of the Drinfeld module, of the endpoints of the Drinfeld module, just as the endpoints of GA, such that the Drinfeld module action at A gives it. So this guy has a module structure, is an A module. Actually, it's finite free. And this cardinality is like what one could expect. So to say, it's like it's the norm of A. Just let me recall Q is A. So then one can take like the in scheme, which is just like a fancy word for the union, where all A of these guys, and get like the torsion. So you denote this as D torsion. All right, again, like
You in the Conway's case now or in the general case?
here I am in the general case.
Q to the R times the degree?
Q to the R times the degree. Thank you. Thank you. Thank you very much. Yes, here there is the rank. Yes. Right, we need to keep track of the rank. Yeah. So the C, the C infinity points of this guy now are just described by F times the lattice defining in correspondence with the Drinfeld modulus modulo the lattice. And so this is like familiar to the situation. Okay, so oh, I have more experience here. Okay, so I said before that like we need like an upper bound and a lower bound. So the Galois lower bound which I will call like master-like. Same as in the classical case for abelian varieties studied by master, and this in our case follows from the work of Breuer. Says that there exists two positive constants depending on the Drinfeld module and on the field of definition, C and eta, such that for every x torsion point order A in L, we have that the extension, we suppose like is defined over L. This is bigger or equal than C divided by the order, the norm of A to the eta. Okay, and so eventually this was essentially already in the literature, and we're gonna use it like relatively soon. And then of course, since the Galois orbital torsion points are still torsion points, we can argue in the usual way. So
can I interrupt? So this is for Drinfeld modules of any rank.
yes,
C and eta depend on what?
the Drinfeld module
On
and the
the
field of
rank
definition.
and on the field of
Right,
definition.
the rank and the field of definition. Yes, right.
So I'm assuming for rank 1, this is more or less obvious because the extensions are abelian and well understood. But for higher rank, this may be more complicated.
Right. I think it was known for rank 1. But yeah, for abelian classical theory, it doesn't make out, it's essential.
C depends only on the field of definition and
The rank.
the rank. It does not depend on the height of the specific RX model as it does in the classical case.
No, yeah, C and eta depends only on D and L.
Well, I believe, but also you're saying also C. Yeah, I mean also C depends only on the okay.
I think so.
It might depend on the height. It depends on the entire D.
Yeah, I mean, classically it would depend also on the height, maybe conjecturally not, but in known results for abelian varieties it depends on the height. No, I mean height of the Drinfeld module itself. But I mean, okay, we have a fixed Drinfeld module.
Perhaps, yeah. Well, eta for sure depends on the rank and on the constant.
Okay.
Let's put a question mark here. Okay, so this was like lower bound. Now we go describe how to get like the upper bound. And for this, we need a rigid analytic pumping theorem. I call R Pila-Zannier. And it's by the work of Gal and Miaro Kato. Okay, so rigid analytic, it means like we need to work in the category of rigid spaces, state, and so now we will denote by curly B an affinoid FQT algebra. So in general, if I have a rigid space, which locally would be the spur of this affinoid algebra, I will denote its algebraic part as like the union of all positive dimensional closed algebraic subsets. And of course, like the transcendental part as the complement of this in X.
So is this like a real algebraic part? Are these algebraic over F infinity or just over C infinity, or is there no difference?
No, there is a difference. There is a difference. Here we are working over well, we want to work over classical points, so F infinity actually. Working, yes, such a setting thing, yes.
So they're algebraic over F infinity.
Yes.
Yeah, no, I mean, as you know, as in the usual case, in fact, the algebraic part you can remove just things that are defined over F, like blocks in classical periodic, it's the same.
Right, so I define for B, we define like the F rational points of fixed height H as like obviously the intersection of spur of B with F, Q, T, some dimension N, depending on where we are working, and we just ask that like the height in the sense of the maximal degree of the xi, x1, xn is bounded by H. And this is like rather classical. So classical form of the theorem says that cardinality of the transcendental part here is bounded by a constant depending on B and epsilon times H to the epsilon for every epsilon, of course, bigger than 0.
I think you should normalize the height. It should be Q to the
Yeah, Q to this. Right, according to our law.
Yeah.
Okay, so this is quite like similar to the classical version of, although the proof doesn't use any ominimality because ominimality is not available in this setting, and it relies mostly on the third normalization theorem. But yeah, and in fact, this is not exactly going to be enough for what we want, but we're going to use remark. We will need a block version, a refinement in blocks, where blocks is going to be algebraic, of course. Well, we can assume irreducible, although algebraic components of certain fibers of the space where we will count eventually above some classical point. Classical, I mean a rigid point, yes. And also the counting one will give us a unit constant. So the other ingredient we need is transcendence. In particular, the version of Axel-Lindemann-Weierstrass for the Drinfeld exponential. I'm gonna discuss. So Axel-Lindemann-Weierstrass for the Drinfeld exponential in the case of dimension 2, so the product of two Drinfeld modules. And now we are working to generalize this. So let V be C infinity algebraic subvariety of the product of two Drinfeld modules of the same rank. And we will take W to be the pre-image of the Drinfeld exponential of V to be maximal and irreducible. So the picture, of course, is like this Drinfeld exponential, like the copy, the diagonal copy, which goes from G8 in infinity square to this product. And we take something here, we pull it back here. We take something maximal and irreducible. Our idea. And then the exponential of W is weakly special, which means is a translate of a sub-Drinfeld module. So recall it's just something which is like connected, algebraic subgroup, stable under the action of the Drinfeld. Okay, so one difficulty here again was like that minimality was not available. So I want to give an idea of the proof. Yeah. So, okay, we make the usual assumptions. So we suppose that dimension of W is 1. So it's an irreducible curve. And we also assume it's neither horizontal or vertical. It's just nor vertical. So essentially we just ask that the projection to A1 in each coordinate is not dominant. And now for the proof, I will, for the idea of the proof, I want to discuss only the Karlitz case. So rank 1, and actually normalize such that the lattice consists just of polynomials. For the concept, it's essentially the same, but we simplify a bit the to get rather cumbersome. Write it down. Okay, so we suppose that W is defined by the zero locus of some polynomial f. And we want to study we want to understand when this guy is can be a subgroup. So what does it mean, a subgroup of GA square in positive characteristic? It means it has to be given by a P polynomial. P polynomial in two variables means that it is given by something like that, where these are all powers of the Frobenius, which means AI, X, Q to the I. This is the definition of a P polynomial. And of course, these guys are additive, so they give a subgroup. So to show that that our F has to be of this form, the first step is some monodromy argument, which essentially says that you essentially use the fact that the Drinfeld exponential, but the Karlitz in this case, right, has kernel exactly lambda and it's additive. So if we translate by a polynomial now, it's gonna be, if we translate the x variable, this is just gonna be x. But locally we can write this y, locally it's a function in x, and it has finitely many branches because it's not the right relation. So the monodromy action is gonna just permute these branches. And while here downstairs nothing happens because kernel plus additivity. So we can say that lambda in some sense parameterizes permutes the branches upstairs. So So the point is that now passing to a finite index sublattice of lambda, sublattice here is just an ideal because lambda equals A. We get that like the permutation becomes trivial, which means that for every lambda in this ideal, by the way, this is a PID, so an ideal is literally just like f times A, just generated by some polynomial f. But so for every polynomial in this ideal, shifting x by lambda corresponds to shifting by mu of lambda, mu is homomorphism, it still is in the lattice, the variable y. Therefore, essentially we get like two finite index ideals, one for each variables, and such that once we intersect our curve with A times A, and we project, and the projection must be onto a finite index ideal on both coordinates, of course. It's like for the x and for the y. And then using like, translating W so that the origin is inside, we reduce this form. So now we know that W is a subgroup. But of course, subgroups in positive characteristic of GA can be of like various degrees. So now we need to rule out certain subgroups that wouldn't give us like Drinfeld submodules. Yeah, so both polynomials. So we do that by counting. The first counting is to show that the degree of P must be equal to, or better, that the degree of P divided by the degree of Q must be in the two ranks, which are equal, so it's 1. So this is to exclude situations, and this is like the example I want to discuss, like the graph of the Frobenius. Like this. Okay, Q, but it doesn't really matter. So once we take this intersected here, we just get A to the P. And of course, the projection on the first factor is all right, but on the second one, they're just fifth power. So in the second factor is just like, let me write it in this way, 2 to the P, which is way too sparse, and it does not contain any finite index ideal. So we get a contradiction, and this shows that the degree must be the same. And then there is the second counting argument. Of course, here for Carlis and for this example, it's like rather elementary, but with more periods, I mean, with higher rank, it becomes a bit more cumbersome, as I said. Okay, and then there is like the second counting step. So we want to get something linear eventually. So here we want to exclude situations like y to the p equal x to the p plus x. We want to rule out this, and then combining with the first step and this, it will have to be linear. And so we get like also a description of our, and then basically we conclude. So here is also just sketch like the idea. So we want to remove the pth power. So we define as z to be x minus y. And this, by some simple substitution, we give that x is z to the p and y is z to the p plus c. Okay, so now we cancel the power and we show that this compresses the lattice in some sense. So every point xy in the intersection, for every point is determined essentially by a z, which has to be a polynomial, such that y equals z plus z. And now we count sizes. So perhaps I will just go here. Count sizes. Okay. If the degree in T, of course, of y is smaller or equal than D, then the degree in Z will be smaller or equal than D over P. And therefore, every y which is admissible, which means it lies both on the curve and on like the product of the and on A squared on the lattice, will come from a much smaller, has to come from a much smaller Z. Okay. But again, the number of possible Z of size smaller at most d to the p is q, it's more or less like almost like q d divided p, while the size of y in a finite index here of size smaller or equal than d, it's like q to the d. So yeah, so we don't have enough z to produce the y by comparison. And this is essentially like the rough idea for this simple example that I wrote here, which also excludes, so if you have pth power, this compresses the lattice, cannot happen by the counting argument. And so W is linear. And this essentially concludes like, this is how we get this Ax-Lindemann. So monodromy plus counting. Okay.
But in some sense, compared to the classical situation, it is a rank one thing. This is more similar to characterizing bi-algebraic subvarieties, right? It's not quite an accident. You have something one-dimensional upstairs.
Lindemann-Weierstrass, well,
No, it's true. It's only for, because it's only for curves in
Yeah, downstairs.
Yeah, I mean, what one believes is what you wrote in arbitrary dimension. We're working on it, but it's like a baby case. So yeah, it's more like a algebraic sense for this baby case.
Okay.
Yeah.
No, just to check whether I was following.
Okay, thank you. So,
And so you also have them only when D is kind of isogynous to D prime. I mean, so these linear things are.
That's not isogynous.
Yes.
Well, they must be. So you have D and D prime, right? Two rank one things.
oh yeah, of course, homomorphism means isogeny for Drinfeld modules.
Yeah, exactly.
Right. So there is like, and they have to have the same rank. So you cannot have an homomorphism between things of different rank, like elliptic curves and GM. And when they have the same rank, they're also isogynous.
They're okay.
They're also isogynous automatically, yes. Yes. Right, thank you.
Did you use here that they have the same rank in this?
Yes, yes. There are one can cook up counterexamples, but I use it here. Yes, it's here that they have the same rank. If they don't have the same rank, no way this works. Like
It's kind of a counting argument. So when you count, the rank enters this count.
again, one can take like this and show that it wouldn't work. Then you apply the Drinfeld exponential, exponentiate to p, and you would find again by counting argument that something.
So what does that mean if they have different rank? That
Well, it means
you can't
that
prove it, or that it really fails, or that there are no
I think that there are
algebraics?
I mean, yeah, because it's quite natural to take like an elliptic curve times GM, for instance, and then to have the same thing.
Yes,
Yeah,
then there'd be nothing.
right. But here seems to be like, this graphs of Frobenius that seems to kill like such situation. But
Well, the thing is that this cross product of Drinfeld modules is not a very natural object in the category of T motives of T modules are understood. You could take their tensor product, or you can take a higher dimensional T module.
Yeah,
Talk about Drinfeld submodules of that, so.
because here actually the phi that they wrote
Yeah.
goes from A, that's the phi is like for a product, right? It goes from A to 2 by 2 matrices here. So this is just like the diagonal case, while what we were saying would be like a more complicated picture.
You would be, but that would be a more natural object to embed your Drinfeld module in my opinion.
Yeah, and such an object should correspond to abelian varieties, at least when it's uniformizable, at least when
That's another problem.
Yeah, because like
Not uniformizable.
here all Drinfeld modules corresponds are like the C infinity points are C infinity module of the lattice, but for Anderson modules, what you like T motives,
You can assume they are uniformizable and work with uniformizable.
yes. But then actually there were counterexamples back in the days from a student of Denis, where one has to assume extra hypothesis, not to get counterexample of Manin-Mumford.
Oh,
Yeah. Okay, so now I wanted to say much more, but let's see. Let me just give like a rough idea of how to get Manin-Mumford from this. As I said, Manin-Mumford was formulated by Denis in the 80s, proved conditionally, and then unconditionally by Scanlon for products, Drinfeld model. So yeah, this is like the usual statement. We have an irreducible closed subvariety of B times D prime C infinity, and I assume the same rank if it contains infinitely many points. Then we take the intersection with the torsion points, and we say that like if the Zariski closure of this guy in V equals V, so then V is a torsion translate V special. So it's a torsion translate of a sub-Drinfeld module. Okay. So, the idea, of course, is that as an aside, there is like one twist perhaps that like, although we are counting points here, of course, we will need the block version of the counting theorem. Because here we don't have the Betty coordinates. So at some point we will need to introduce a parameter space and some linear map whose fiber are higher dimensional and where our torsion points will live. And so there we will need like to count like these guys are algebraic, fully algebraic. So we need to count like there. So since I also want to say a few words about André Oort, I will be very, very brief. So we take an X torsion in the Drinfeld module, and we denote by Z is exponential. It's image under the exponential. I will call two bases of lambda and lambda prime by Ci and Ci prime. So actually we can we can find all our torsion points. The pre-image of all our torsions will be included in some affinoid ball, well, admissible ball. Actually here it's even affinoid, some affinoid ball, and then we will intersect this ball with the pre-image, the pullback of V via the exponential. We will call this guy V tilde. So now we can write Z as just like linear combination of the periods. Both of them are I prime, prime. And by this ball, we can assume that like these guys as like order at infinity positive. So as I said before, we need a replacement for the Betty coordinates. And so we will introduce 2 times R C infinity, a parameter space for the coefficients, and the linear map, which will go to G A squared. Well, we will just take like these guys, A1, AR, A1, A1 prime, AR prime, and send them to the linear combination. So, okay, this fiber, like, yeah, and the fibers, of course, are positive dimensional of this map. And is not why we will need to use Pila-Wilky. So in particular, we will define this space. We'll take our vector in some data algebra. Maybe I should call it data, but it's like a disk. So, and we're gonna ask that, like, via this map, our vector will be inside V tilde, which is the intersection of the ball, the pre-image of the explanation. Okay, so in few words, now the rigid analytic, Wilkie produces some blocks here, actually in some fibers, but it's okay. And then we divide two cases. We consider the restriction of these two of our map L to the blocks, and if it's constant, then they're just points, and we can apply Pila-Wilky. We get an upper bound combined with Masser-like lower bound. We get a contradiction, and that's all. Of course, we are working by contrapositive here, so we're supposing that D contains infinitely many points, the risky dense set of points, but it's not special. But if this guy is not constant, and we take its image, it's a Zariski closure, we'll consider this to be W, and since this guy will be in the pre-image, and we can hook it up so it's irreducible, maximally irreducible, then we can apply our Ax-Lindemann and show that like it's almost like a conclusion, this, because like this guy is like positive dimensional, it is dimension 1. So this gives a contradiction, because by Ax-Lindemann Weierstrass, then V would contain like a translate of a sub-Drinfeld module. This is impossible, which means that which gives a contradiction. The contradiction is at the level of the dimension of B. So B is going to be zero dimensional. We can take it irreducible, so it's going to be a point. And again, like, it gives like the bound we need. So in the last, if there are questions, please interrupt. I know it was very sketchy, but so perhaps I should say a few more words about the block version. The block version says that like the F rational points of a bounded height are contained in certain fiber of our curly X, and the number of these fibers will be much smaller than the height to some epsilon. And these fibers are the block. Well, actually the block are they're reduced. Well, yeah. And then they may have different irreducible components, but we can reduce to 1. Therefore, if these guys are just points, okay. So, what about André Oort? Again, also here we have like this baby case of dimension 2, means for C A2 of C infinity. But we're working to generalize. So, rigid analytic, right? So the things here are rather different, where the Drinfeld opera space, in this case just a plane, and these are really interesting objects with a lot of like fascinating model interpretations. And in this case, it's just defined as like the Poincare Aperov plane. Taking our points here, we get a lattice, of course. So we get the Drinfeld module of rank 2. And then there is a J function, which is defined in terms of like the coefficients. So if this guy is T plus G tau plus delta tau, well, G and delta are modular forms actually in Z. And this guy also is like This guy, the J, is a modular function in an appropriate sense, of course, but it must be, everything must be done rigid analytically here. So eventually, the J invariant of Z will be the J invariant of the Drinfeld modules. It will be just G to the Q plus 1, really that. Okay, so here also we have a GL2 of A action. It's very similar to the classical case. And so once we mod out by this, we get an isomorphism. And this is the coarse moduli space of Drinfeld modules of rank 2 up to isomorphism, of course. The Drinfeld module of rank 2 over C infinity with no level structure, which as usual doesn't matter also in this case. Okay. Again, by analogy with elliptic curves, there is like a good CM theory. So when you say that this guy has a CM, if it's endomorphism ring, it's big. It means that it's given by some order in a quadratic field. And there are similar theorems of Shimura. So let's say that like this is an order inside K, CM field. So if we add here the value, the Galois group of this guy is isomorphic to the Picard of OC, and therefore, we get the lower bound simply by Siegel. Okay, bonus is effective because of GRH.
It's the same Siegel.
It's the same, literally the same Siegel, just effective for free. But we don't really mind about this, just like small bonus. All right. Of course, like, and oh yeah, so by Siegel, let me write it. So this is much bigger than the discriminant. You take the absolute value, right? Because this is a polynomial. When I write d of C, I mean fundamental discriminant times the conductor to the square. You also have 1/2 minus epsilon. So our limitation here is also, we also have like an hyperbolic Axel Lindemann. Axel Lindemann, yeah. Not Weierstrass, because for the J. And so for now, we have only in dimension 2. So the proof goes through similar lines. Like the idea of the proof is very similar to the one of like Axel Lindemann Weierstrass. We use some monodromy, and then we use some counting argument in a rather analogous way, obviously, mutatis mutandis. So let me like sketch also the proof here, which has like some interesting twist of André Oort. André Oort for A2. This was already like obtained by Breuer by adapting the proof of Edixhoven for general N. And we both need to assume actually that P is odd. There are some technical problems for P even, unfortunately. And yeah, okay. So the idea is that we take, I will not recall the statement because like it says that we know it. It said that like a curve, an irreducible curve here has infinitely many CM points if and only if is special, which means that either it's vertical or horizontal with a CM, or it's the graph of the modular polynomial. So it's the graph of an Hegel correspondence. Everything is defined by analogy exactly as for an elliptic curve. I mean, yeah, exactly is a bit heuristic. Okay, we take a CM point given by Z, which is a quadratic point, and we want to work in a quadratic fundamental domain. So yes, there is a theory of quadratic fundamental domains here. But again, we assume by contrapositive that C, that our curve C is not special, but contains infinitely many CM points. Okay, so there is like a bound on the height of this quadratic point, just given in terms of the discriminant. And actually, it's here that like the P equal to case fails because we don't have such a bound. If we assume like not even for every in every case for P equal to, but like if we take P equals 2, then we don't have this bound anymore. It's not bounded. This guy can grow and like then yeah, at any rate, phi is not this F, fundamental domain is not an affinoid. And of course, you can imagine it's very far from being bounded. And for our Pila-Wilke, we need to reduce to a bounded situation. So although the picture is not exactly accurate, you can think of something like that. And we want to see that not too many points go deep into the cusp. So we want somehow to stop at some point, then to cover this guy with some, like a reasonable number, depending on this height of balls, and then counting here uniformly. Okay, so a bit more technically, so how do we do that? How do we stop? One way would be to prove equidistribution, like a Duke's theorem, which is possible, of course, but we use a different technique. So we take the analog of the faulting height, which is called the Taguchi height of a Drinfeld module. And again, here is defined essentially in a very similar way. Is the degree of some metrized line bundle. I will not recall the definition, but it shares many properties. And for this, there is a Colmes formula. So let me underline that the average Colmes conjecture has not been established for T modules, only certain cases. Yes, well, yeah, I will conclude. There's a Colmes formula, and from this Colmes formula, essentially, we can bound the Taguchi height in this way.
It's a known case of the Colmes.
This is a known case for Drinfeld modules of any rank. It's known, not on average, right? It's known like for elliptic curves. The Colmes formula is known. I mean,
You wanted the height to be distributed to the epsilon?
right. Thank you. Thank you. Yeah, yeah. By the work of Utsunwei, this is known, and so we get this bound. Moreover, this is very close to the veil, logarithmic veil height of the J invariant. And so now we can like really, and since this grows slowly, we can cover with certain balls. Most of the conjugates will be here. There are balls with enough conjugates. We can apply Pila-Wilke. Of course, there could be other points here, but it doesn't matter because we get a uniform constant, even if we don't have anything like cominimality. And at this point, essentially, we argue again by contradiction, and we can conclude. Yeah, that's all. I think I can stop here.
Yes. Questions?
So how important is it to you that work with Drinfeld modules to find over a PID? Can you do general A?
We didn't try, but I do believe so, because like some crucial ingredients like the Colmes formula is known in all general, like for Drinfeld module of any rank over any A. So our A, right, let me just recall that our A is FQT is just like the H0 of P1 minus infinity and then regular functions, right? For this guy over FQ. So if we take another curve, which is geometrically connected, irreducible and smooth, we can get like more general rings, but the Colmes formula is there. So I think that should be.
How about the rest of the arguments? I mean, did you ever use the fact that this FQ bracket T
No,
is
well,
a PID?
Are there analytic uniformizations in this?
yes,
Everything is fine.
everything is known.
fine.
Yeah,
For
true.
Drinfeld modules, yes, it's fine.
No, I mean, one point where perhaps I use it is when I show, yeah, maybe one point where I use it is when like we show that like the Taguchi height is close to this guy. This is like just mimicking, like reproducing a classical result of Silverman on the Book of Cornell. So perhaps there it's used, but it's not, I hardly believe it can be substantial. Substantial is T, different from 2, unfortunately. The oddest prime.
Your proof of Axlindem and Weierstrass is just based on monodromy. Does it use a differential that you do?
All right. So no, we in this case it's like so Axlindem and Weierstrass and the hyperbolic version they use no differential structure at all. We just use the monodromy to reduce like the subgroup or to the analog of that for the Drinfeld.
But there is a differential equation?
No.
No?
No differential equations involved.
No, I mean,
So
there are differential equations, we don't use them, but
But then-
heuristic P, you have to, like, for example, the derivative of X P is 1.
Right.
Yeah.
So, I mean, if you want to use differential equation, you should somehow
As a Schmidt.
as a Schmidt.
So yeah, in the work in progress, to generalize the transcendent results to higher dimension, then we need more.
Yeah, we do believe that this differential machinery should work, but we are still trying to generalize.
Was it crucial to have like two D prime and like here A1 times A1, or can you do more self products everywhere?
So the problem of like we work in dimension, I expose in dimension 2 because the transcendental, the functional transcendence we have for now written down are in dimension 2. But yeah, we're working for that, and that's the only obstruction actually to the dimension.
But and here for André, can you?
And for André also because like we will just take like the product of A1s, right? So actually there is something quite interesting. Like of course the products of like A1 times A1 times A1 is isomorphic to A3. But I mean, not discovering the hot water. But here actually these are like triples of like if we also want like the Drinfeld module thing, here we just get triples of rank 2 Drinfeld modules, and here we get like Drinfeld modules of rank 3. So it's different. So this would be the moduli space of rank 3 Drinfeld modules, and it's called the Drinfeld modular varieties, which has no counterpart in the characteristic 0 board. So this is not like AG or something. Like it's not. Yeah.
Any other questions? Okay, thank Francesco.
Thank you.